Assalamu alaikum wa rahmatullahi wa barakatuh. The shape of a molecule has a very important impact on the intermolecular forces between molecules. Now, before we continue, we must differentiate between intermolecular and intramolecular forces. Intermolecular forces occur between two molecules. So if you look at this case, for example, we have a water molecule and another water molecule. So intermolecular forces will be the force between this water molecule and that water molecule. So it will be the force between this hydrogen and this oxygen between two different molecules. But when we talk of intramolecular forces occur between atoms inside a molecule. So intramolecular forces will be the force between the hydrogen and oxygen within one single molecule. So the hydrogen and oxygen force here would be an intramolecular force, and the oxygen and hydrogen force here would be an intramolecular force. But the, the molecular force between this hydrogen and that oxygen, between that two molecules, different molecules, will be called intermolecular forces. So we're going to be discussing intermolecular forces, forces between two different molecules. Now, continuing, the first type of molecular force which we will be looking at, and that is the strongest intermolecular forces, will be hydrogen bonding. Now, hydrogen bonding occurs when hydrogen is bonded with an atom of very high electronegativity. So oxygen, nitrogen, or fluorine are atoms that have a very high electronegativity. So when these molecules, these atoms combine with hydrogen, we see that the electronegativity of the oxygen molecule, in this case, for example, is so strong that the electrons are very dense in the vicinity of the oxygen and very sparse in the vicinity of the hydrogen. And we see that the bond between this hydrogen, which is quite positive now, and this oxygen, which is quite negative, is very strong, so much so that the bond is extremely strong, that it is almost as though this hydrogen is bonded to that oxygen rather than the oxygen that it is attached to originally. So this force between the hydrogen and the oxygen is called hydrogen bonding, and it is the strongest intermolecular forces that are known. So in this case, we see that we got hydrogen bonding taking place between the hydrogen and the oxygen, and those are the forces that are between the molecules, intermolecular and not intramolecular, as we said previously. So hydrogen bonding is the strongest intermolecular force, and we can see this diagram here as well, where the hydrogen bonding occurs there and there. So the three most famous examples of hydrogen bonding occurs between water molecules, ammonia molecules, and hydrogen fluoride molecules. And because of the intermolecular forces, it affects the physical properties of the substance. Things like boiling point, melting point, viscosity, vapor pressure. Those things we won't discuss here, but we will just be discussing the type of intermolecular forces that are found between molecules. Now, another example of an intermolecular force will be found between an ion and a dipole. So here we have water, which is a dipole or a polar molecule. And as we discussed previously, we know that water has an oxygen side, which is slightly negative, and a hydrogen side, which is slightly positive. So when we have the water molecule coming into the vicinity of sodium ion, we see a bond takes place. So for example, if you take table salt, NaCl, and you put it in water, we see that the table salt dissolves readily in water because table salt is made up of Na plus ions and Cl minus ions. So here we have the Na, which I have written as a positive ion here at the bottom, And if you look at the water, it is a polar molecule, it is a dipole. So the oxygen side is slightly negative and the hydrogen side will be slightly positive. So to draw it, instead of you drawing the molecule each and every time, we can just draw an oval structure with a delta minus and a delta plus to depict which side is slightly negative and slightly positive. Now we know that opposites attract. So if we have a positive sodium ion, then the negative part of the polar molecule will be attracted towards it. That's why we'll see that the oxygen side of the sodium will be attracted to the oxygen side of the water molecule will be attracted to the sodium. It wouldn't be the other way around where we get the hydrogen side attracted to the sodium. It will be repelled so that the oxygen side is attracted to the sodium because the negative part of the molecule will be attracted to the positive ion. Similarly, we know that chlorine is a negative ion. So if we look at the oxygen, its negative side is the oxygen side, and the hydrogen side is the positive side. So in this case, we will have repulsion, and the molecule will reorientate itself so that the hydrogen side, which is positive, will be attracted to the chlorine, which is negative. So in this case here, we see that chlorine is negative, and the slightly positive side of the dipole will be attracted towards the negative ion. And in this case, it's the hydrogen atom, in the hydrogen atom in the water molecule. So this is an example of an ion dipole force that exists between molecules, and we see that in this case the sodium chloride will dissolve quite readily in the water. Then the third example we will look at is when we have iron uh, in an induced dipole. So if we have, say, CCl4 carbon tetrachloride, which is in solution, and we place NaCl in this carbon tetrachloride solution, then we'll see that the salt, the table salt, the NaCl, does not readily dissolve in the carbon tetrachloride solution. And the reason can be seen here where we take this example where we have chlorine, which is a negative charged ion, and we have I took NH4, which is methane, which is a gas, but it has the same structure as carbon tetrachloride. Now, when we look at this NH4, this NH4 molecule, it's a symmetrical molecule, and it's a non-polar molecule. There isn't a negative side to it or a positive side to it. So when a negative charged ion comes into contact with a non-polar molecule, we see the case here that it doesn't readily dissolve because the electrons are evenly distributed in this non-polar molecule. But because of the collisions, what happens is that we have an induced dipole that is formed when we get a slightly positive side that is attracted to the ion and a slightly negative side that is repelled away from the ion. So we get an induced dipole where we force the molecule which is non-polar to become slightly polar so that there is some type of attraction between the ions in the solution and the non-polar molecule which has become an induced dipole for a short while. Now, another example which we could have is a dipole-dipole structure. Now, this one will be easier to work out because we see the case where we have HCl. And HCl, we know, is a polar molecule where the chlorine has a higher electronegativity than the hydrogen. So the electrons are more in the vicinity of the chlorine. So the chlorine side is slightly negative and the hydrogen side is slightly positive. So if another HCl molecule comes into contact or comes nearby another HCl molecule, the chlorine which is negative will be attracted to the hydrogen side, and we get a dipole-dipole forming where they are connected. And we can depict it using this diagram here below, where we get a dipole-dipole structure. The positive is attracted to the negative and vice versa. But if, for example, the HCl comes this way, because the chlorine and the other chlorine is negative, we'll see there's a repulsion and the molecules will orientate themselves in such a way that we have a dipole-dipole force that is formed. And that's why we see that a polar liquid will dissolve in another polar liquid. For example, ethanol, which is an alcohol which is polar, will dissolve readily in H2O, which is also polar. So we see that like dissolves in like. Another example which we will look at is when we have a dipole and an induced dipole. Now, the induced dipole we spoke about earlier is something that it is forced, that the dipole is forced onto the molecule. So here, I'm just looking at an example, a theoretical example, where we have HCl, which is a dipole, and we can show it using this oval structure where the chlorine side is slightly negative and the hydrogen side is slightly positive. So let's just reorientate this so that we have that. So the chlorine side is negative and the hydrogen side is positive. Now, if we have carbon dioxide, which is a linear structure, and carbon has a lower electronegativity than oxygen, then we see here that we have a case where the molecule looks like this now at the moment, where the carbon side is the oxygen side is negative, and we see that the carbon, which is in the center, will be slightly positive. So this orientation of the electrons will be in such a way that the outer edges of the molecule will be negative and the center will be positive. So when the carbon dioxide will come into contact with the HCl, then because the side closest to it is negative, what will happen is this negative will be repelled onto the other side, and it will be an induced dipole where the side nearer the chlorine will become positive and the side further away will become negative. So in this case, we have a dipole, induced dipole, uh, intermolecular force which is formed, and that is a weak force. And another example that we will have is London forces. Now, London forces take place between two nonpolar molecules. For example, one carbon dioxide and another carbon dioxide molecule. Now, because both molecules are nonpolar, we see that there is a negative side to the molecule and a positive side to the molecule. But what occurs is that when the one molecule collides with another molecule, one side momentarily becomes positive and the other side will become momentarily a negative. And as a result, we see that we have a momentary dipole forming. That we have an induced dipole force that is forming, and for a short while we see that we get extremely weak intermolecular forces that are formed, and those are called London forces. And the example of carbon dioxide, as dry ice. If you look at dry ice, we see that dry ice is has extremely weak forces between them, where even at room temperature, we see that the dry ice already sublimates from the solid phase. It goes directly into the gaseous phase. It skips the liquid phase. And that shows that the forces holding the dry ice crystal lattice together are extremely weak. And as a result, the carbon dioxide molecules readily move away from each other. So we see that hydrogen bonding is the strongest intermolecular forces. And then we get van der Waals forces, ion-dipole, ion-induced dipole, dipole-induced dipole, and the weakest force that we will get will be momentary dipole forces, which we call London forces. So here we've discussed intermolecular forces, and we've realized that intermolecular forces play a very important role in terms of the physical properties of solutions and structures, where it affects the melting point of a structure, the boiling point of a structure, the viscosity, that means the resistance to flow of the structure, the flow of the liquid. For example, oil flows at a slower rate than water, so we can deduce that oil has greater intermolecular forces than water. That is why it has a higher viscosity, and it also affects the vapor pressure, where we see that how readily a liquid vaporizes. So that will be a summary of the different types of intermolecular forces that we have. Thank you very much for watching.